Okay, so this is a special session of the VPH Summer School. So the Virtual Physiological Human Institute, that is now called the International Society for In Silico Medicine. So as the name indicates, it's a scientific society. And it promotes basically then in silico medicine internationally, from the research side to the industrial side. So there is, you might know, the VPH Institute, which is what has been rebranded as the International Society for In Silico Medicine. And then there is the Avicenna Alliance, which is the corporate arm. So VPH Institute is a research part, and Avicenna Alliance is industrial part. So the society is basically promoting in silico medicine in several ways. So first of all is obviously then the gathering of the researcher in a biannual congress, which is a VPH conference. So it's all even years. So the next VPH conference will be held in 2026. And it will happen in Italy at the Politecnico di Milano. So that's really a great place to see the convergence of all what I have mentioned before at the opening. So you have machine learning, you have artificial intelligence, you have biomechanics, you have biophysics, you have computational biology, you have bioinformatics, and applied to an extremely wide range of fields, as we have here at the VPH Summer School. And you have an important part, which is then the corporate part. So at this conference, you always have industrial sessions, which are not the typical industrial sessions where people come and show their product. They are really industrial sessions where you have corporate professionals who are explaining how they cope with barriers, with the adoption of in silico medicine. So market barriers, regulatory barriers, especially in the regulatory where the aspects, there is a lot to do because it's almost a virgin field. And then, of course, there are a lot of startups and spin-off. It's also a great opportunity then to talk about fundings, fundings, investors, which is also the characteristic of a lot of emerging fields. Among these corporates, you also have well-established multinational companies. You find Medtronic, you find Stryker, you find Johnson & Johnson. So it's also nice then to see what is the vision of the startup compared then to the vision of these giants of the healthcare industry. So that's how basically that's the kind of benefit that the society is providing to its members. And then there's specific activities for the most junior members. So in general, people start to be member at the master level or at the doctorate level. Of course, you can also then become member at the bachelor level too. I think that with the registry, with the VPH Summer School, so basically then you have the right then to become member and to have 1-year membership if you're a PhD candidate. And then as part of this membership, so you have a series of keynote webinars that you can attend for free. And you have an entire program of awards. So you have awards at the conference, so the best paper award at the conference, the best poster award at the conference. Now there are also mobility awards then to promote then so it's financial support basically then to the travel of the members. And there is, so the most important award of the society is basically the VPHi Best Thesis Award in silico medicine. So here it's my pleasure then to announce that Elena Redaelli is a winner of this year's edition. It's quite a competitive award because you have among the panel, so you have a representation of senior researchers or of professionals that actually represent a bit then the composition of the society. So people are looking at the PhD thesis both from the basic research part or basic technological development part, but also from the perspective of applicability, impact, so much more projection into the real world. So, so then Elena has won the award this year, and she will present now. So just to give you an overview of who Elena is, she's obviously a member of the VPH Institute. And so she's postdoctoral research fellow right now at the Instituto de Óptica Daza de Valdés en el CSIC, está aquí, en España. She graduated in biomedical engineering in 2021 at the Politecnico di Milano. And in 2024, she got her PhD in biomedical engineering by the University of Saragossa through the European Marie Sklodowska-Curie Network project that was called Oberon. And so she specialized in structural fluid dynamics and fluid structural interaction modeling for nonlinear mechanical problems that she's applying to corneal tissue. So this is what Elena will be presented. And then, so she has then combined so this physics-based modeling, so with machine learning and artificial intelligence. So now I will stop the spoiler, and Elena, I will leave you the floor.
Okay. Thank you very much for the nice introduction, and I'm sorry to attend online. I would like to be with you there in Barcelona, but I hope you can enjoy anyway my presentation. I would like to thank the scientific committee and the VPH Institute for awarding my thesis with this prize and for inviting me to this webinar. In this keynote, I will presenting my doctoral thesis titled Characterizing Patient-Specific Corneal Biomechanics, High-Fidelity Modeling, and Artificial Intelligence Techniques, which I carried out at the University of Saragossa under the supervision of Professor Jorge Grasa. As it has been said, my PhD is part of a European project called Oberon, Opto-Biomechanical Eye Research Network, which involved several institutions over Europe. This gave me the possibility to interact with other institutions over Europe with different background. And in particular, I had the possibility to spend some period abroad, in particular at the Wrocław University of Science and Technology in Poland, at the Politecnico di Milano in Italy, and at the University of Bern in Switzerland. The duration of this PhD has been of 3 years, and the main objective of this European project was to fill the gap between two key fields, the ocular biomechanics and the optics. In fact, while it is known that the biomechanics and the optics play a fundamental role in the vision and in the eye pathology, the underlying cause of this interaction remain unexplored. And this is where our work comes in. In particular, I was focused on the application development of the knowledge of the corneal biomechanics in order to have more accurate methodologies to predict and diagnose ocular pathologies. So vision plays a fundamental role in our society. In fact, much of the contemporary life is organized around our ability to see. the world we experience, like the picture you can see in this slide, appears clear to most of us. However, for individuals affected by eye pathologies, this same landscape appears different. For example, if someone is affected by keratoconus, this same view would be blurred and distorted. In case of glaucoma, the peripheral vision would be lost, creating this tunnel-like effect. For the many affected by myopia, the vision of distant object would be blurred. So in this presentation, I will discuss the advancement we have made in the field of ocular biomechanics with the underlying aim to restore clear sight to all these people. But let's do a step back. The eye is a complex biological system composed of different parts and layers. In particular, the main objective of the ocular structure is to send the light rays, which are in the outside world, to the brain through the optic nerve. The optic nerve is directly linked to the retina. So the objective of this, all these ocular structure is to refract the light rays coming from the outside world to the retina. And the primary refractive surface of the eye is the cornea. The cornea is the transparent outermost layer of the eye. And when the mechanical properties of the cornea are damaged, that is, one part of the cornea is less stiff than the other parts, the keratoconic pathology arises with this bulging on the corneal surface. The cornea is linked to the sclera, which is the white part of the eye, through the limbus. And corneal limbus sclera gives the eye its structure. When this structure is too long, when we have a longer eye than normal, the myopic pathology arises. One solution to correct the myopia is laser refractive surgery, in which a part of the cornea is cut in order to shorten the eye. All this structure is filled with the humors. The humors are a liquid pressurized at an intraocular pressure, and when this pressure is too high, we have a pathology called glaucoma. So why is it important to study the mechanical properties of the corneal tissue? First of all, to diagnose eye diseases. For example, the disease of keratoconus that is directly related to the mechanical properties of the corneal tissue. But also to optimize refractive surgeries, because as I said, in the refractive surgeries, we cut a part of the cornea surface by means of a laser, and if we are able to estimate the mechanical properties of this tissue, we are able to predict in a patient-specific manner the outcomes of the surgery. In the management of glaucoma, it is important to know the mechanical properties of the corneal tissue, because all the methodologies currently available to estimate the intraocular pressure are indirect. They involve the cornea. So there is a direct interaction between the cornea and the pressure inside the eye. But also to develop new eye treatments, for example, new contact lenses. We have the interaction of the contact lenses with the corneal surface, so it is important to understand the interaction between them. So in previous studies, the other authors have been studying the mechanical properties of the corneal tissue by means of ex vivo test, uniaxial or biaxial. But as you can see in the video, the main limitation of ex vivo tests is that the corneal shape is lost. The humors goes out of the structure, and the cornea is no more pressurized. Moreover, the cornea is an anisotropic tissue because it is composed by two families of collagen fibers perpendicular to each other. So when cutting, these fibers are cut too, and we are not able to study this complex anisotropicity by means of ex vivo test. For this reason, some in vivo techniques have been developed, for example, the non-contact tonometry. In the non-contact tonometry, an high velocity air jet hit the cornea, and in the Corvis ST device, which is the non-contact tonometer, this deformation is recorded by means of an high-speed camera. To summarize what I've been discussing till now, I would like to show you a video. Let me know if you can hear the audio.
Do you really know what biomechanics is?
Can you hear?
And what it has to do with the
Yeah,
cornea?
we can hear.
It's actually very simple. Biomechanics describes how biological bodies react to outside forces. For example, pressure. A distinction is made between elastic and viscous properties. Elasticity is the ability of a body to return to its original size and shape after using force, like a spring. The more elastic a body, the better it is at doing this. Stiffness describes how much force is needed to elastically deform a body. This depends on both its composition as well as the amount of material. Viscosity is the resistance against permanent deformation. Viscous bodies can no longer return to their original state or only do so slowly. The cornea is both viscous and elastic, which means that it retains its form after being exposed to outside forces and only later returns to its original size and shape. A healthy cornea can do this relatively quickly. It's elastic and stiff. In the case of an ectatic cornea, the biomechanical properties are changed. This leads to increased thinning and bulging of the cornea. For example, laser surgery could cause ectasia. The elasticity and stiffness of the cornea therefore have a lot of importance in ophthalmology. For example, in corneal cross-linking, intraocular pressure measurement, or corneal incisions. However, the stiffness of the cornea could never be measured individually until now. Corvis ST from Oculus makes this possible for the first time ever. Pressure is applied to the cornea via an air puff, and a high-speed camera records the change. The Corvis software uses this to calculate a stiffness parameter of the cornea. These data are of particular relevance for screening before refractive laser surgery. In combination with the Pentacam, Corvis ST provides dual safeguarding. Patients at risk with a predisposition for ectasia that can't be detected by corneal geometry measurement alone can be detected by means of corneal stiffness measurement. At the same time, the joint analysis helps in determining if any patient can be operated on safely. On the basis of tomography, some of them would have to be refused surgery due to reasons of safety. Corvis ST therefore helps you to operate on more patients safely and also reduce the risk of an incorrect decision. Oculus.
Okay, so you have also seen the results, but what is the problem of Corvis? I said that an high velocity air jet hit the cornea, and we have some deformation images. But this deformation is the result of the coupling of 4 factors. Not only the mechanical properties of the corneal tissue, but also the corneal geometry, in particular its thickness, the intraocular pressure, and the external load applied, in particular, in this case, the air jet. So the main objective of my doctoral thesis has been to estimate the mechanical properties of the corneal tissue in vivo and in real time from the results of the non-contact tonometry. And to reach this objective, I have been developing an high fidelity model of the non-contact tonometer. Then I will propose a methodology to estimate the intraocular pressure independently on the other factors, and then a methodology to estimate the mechanical properties of the corneal tissue. In particular, going first of all to the numerical model, to model the non-contact tonometry, I have to say that some other authors have been developing this methodology, but some of them used structural simulation. So they deformed the cornea by means of a time-dependent pressure. The problem of this simulation is that in this case, the load applied is not dependent on the corneal geometry and the corneal stiffness. For this reason, the other authors developed computational fluid dynamics simulation to estimate the pressure and then used this pressure to apply a pressure load on the structural cornea. But also in this case, this pressure does not depend on the corneal stiffness. For this reason, the best numerical approach to study the non-contact tonometry and to simulate it is the fluid structure interaction simulation. The currently available studies had some limitation, so I decided to develop a complete framework. First of all, I constructed an idealized model of the eye based on average dimension taken from literature, and I considered the material properties of cornea and limbus anisotropic with this distribution on collagen fibers. Regarding the strain energy function, I assumed the Holzapffer-Gasser-Ogden model, which depends on 3 parameters: C10 describing the behavior at low deformation, and K1 and K2 describing the behavior at high deformations, so taking into account the anisotropicity of the collagen fibers. The cornea, the data we have regarding the cornea are referred to a pressurized cornea. So the first step of our simulation is the development of an algorithm to estimate the zero pressure configuration of the cornea. So the first step is find the zero pressure configuration, pressurize the cornea, and then apply the air jet. The air jet is applied by means of a fluid structure interaction simulation in which the fluid is the air, which with this domain I considered with a specific density and dynamic viscosity, and the velocity inlet is the same velocity inlet of Corvis. So I will show you some results. In this case, you can see the streamlines of the air deforming the eye structure. And among others, it is interesting to note that regarding the air pressure over the cornea, there are some peaks in which the air pressure is negative. This behavior is only visible with the fluid structure interaction simulation. With another simulation, this is not visible. The most important parameter that can be studied in this simulation is the corneal displacement, and in particular, the displacement of the corneal apex is called the deflection amplitude in clinics, and the time at which the deflection amplitude is at its maximum is called the highest concavity point. Here you can see the corneal material behavior. You can see that the behavior in compression and in tension are different. And this is because the behavior is anisotropic. Regarding when we have finished the idealized model, we developed the patient-specific corneal model starting from data of another device called Pentacam, which gives us the point cloud of the geometry of the cornea. So with this patient-specific data, we were able to perform the patient-specific simulation with the same results, the pressurization of the eye from the zero pressure configuration, and then the deformation of the cornea by means of the effect of the air jet. I have to say that the total duration of one simulation is 48 hours on 16 CPUs. So it is not applicable in real time in clinics. But this simulation gave us the possibility to validate the procedure. In particular, we ran 100 simulations with the same corneal geometry, but with different intraocular pressure and mechanical properties. Then we recorded the deflection amplitude. Do you remember the deformation, the displacement of the apex in time? And we found out that the numerical results were in the range, the clinical result was in the range of the numerical result. And in particular, there were 6 simulations in which the difference between the numerical deflection amplitude at highest concavity and the clinical deflection amplitude at highest concavity was below the 5%. Studying these cases, we observed that the case, the one in orange, in which the mechanical properties were stiffer, was associated with a lower intraocular pressure, and vice versa. With the softer mechanical properties, we had a higher intraocular pressure. That means that the same result can be given by a combination of different parameters of mechanical properties and intraocular pressure. And this was like a demonstration of the coupling between the mechanical properties of the corneal tissue and the intraocular pressure. So to conclude this first part, we developed a fluid structure interaction simulation clinically validated to demonstrate the coupling between the mechanical properties of the corneal tissue and the intraocular pressure. You noted that in the patient-specific simulation, we didn't consider the internal structure of the eye, while in the first one, yes, because we demonstrated also that the internal structure didn't play an important role for our results. So once we have a framework validated, we used it to develop a methodology to estimate the intraocular pressure. And in particular, I have to say that in clinics, currently the intraocular pressure is measured or by means of GAT, that is Goldman applanation tonometer, in which a probe loads the eye, and with a contact tonometer deform the corneal surface. By means of a direct relationship between the first applanation point of the cornea and the intraocular pressure is estimated. The other two devices, one is Corvis and the other ocular response analyzers, are based on the same principle. They estimate the intraocular pressure by means of the first applanation point, but the difference is that they apply an air jet, so they are non-contact tonometer. But currently, a methodology to estimate the IOP independently on the mechanical properties of the corneal tissue and on the corneal thickness was still missing, because in these 3 methodologies, we go through the cornea to measure it. So we decided to study, by means of an energetic analysis, the process of the non-contact tonometer. In particular, we studied the work acting on the anterior corneal surface. On the anterior corneal surface acts externally the work of the air path and internally the work of the intraocular pressure. When these two works are the same, the system is at equilibrium. And when the system is at equilibrium, the cornea reaches its highest velocity point because the acceleration is 0. We found out that this point of equilibrium is not the same as the first applanation point. Usually it is higher the time of highest velocity than the first applanation point. So we performed these different simulations with different intraocular pressure to study, first of all, the work of the intraocular pressure at pressurization, so before the air path. We found out that there is a quadratic relationship between the work of pressurization and the IOP itself. And this quadratic relationship is this one you can see in the slide. When considering the air jet, here in these points are the points of equilibrium with the different intraocular pressure. So recording the time of equilibrium, we found a quadratic relationship between this equilibrium time and the initial work of the intraocular pressure, that has these lines. The initial work of pressurization has a quadratic relationship with the time of equilibrium, when the work of the air path and the work of the intraocular pressure are the same. Then we tried to perform other simulations with the same intraocular pressure, but different mechanical properties of the corneal tissue and different thickness. In that cases, the time of equilibrium was always the same. So our conclusion was, okay, the time of equilibrium depends on the intraocular pressure, but not on the mechanical properties of the corneal tissue and the corneal thickness. So we can use these two relationships we found to propose another equation to estimate the intraocular pressure depending on the time of equilibrium, that is the time of maximum velocity of the cornea. So it is a clinically available result. So in this part, we are the conclusion is that we have a new equation to estimate the intraocular pressure that, based on our simulations, it is not influenced by the mechanical properties of the corneal tissue and the corneal thickness. So now that we have a methodology to estimate the intraocular pressure, we can try to estimate the mechanical properties of the corneal tissue. And to reach this aim, we first of all created a large data set of fluid structure interaction simulation of random input parameters. In this case, different geometries, different intraocular pressure, and different mechanical properties in a physiological range. For each simulation, we recorded the corneal displacement, the displacement of the corneal apex, of the corneal anterior surface in time. With this large data set of results, we tried to reduce the dimensionality of our system by means of a proper orthogonal decomposition technique. And we found out that a basis composed of 8 orthogonal vectors is able to explain the 99% of the model. So this basis reduced the dimensionality of our system, but the basis is unique. We need some coefficients which, multiplied by this basis, give us for each simulation, the displacement. So these coefficients depend on the input parameter of the simulations. We used these coefficients together with the intraocular pressure and some coefficients describing the geometry of the anterior and the posterior surface of the cornea to train an artificial neural network with as output the three parameters describing the mechanical properties of the corneal tissue, C10, K1, and K2, that are the parameters of the Holzapfel-Gasser-Ogden strain energy function. Here you can see the validation of our artificial neural network. I mean, in red, you have the mechanical response of the cornea with the parameters used in the simulation, and in blue, the mechanical response of the cornea with the parameters predicted by the artificial neural network. These are cases obviously not used for the training. But how can we use this tool in clinics? Let's hypothesize a people going in clinics and undergoing non-contact tonometry. We have this result clinically, and we would like this one, the mechanical response. We have the information about the corneal geometry by means of the pentacam device, which is always performed. With this information, we can estimate these Zernike coefficients describing the corneal surface of the patient. With the velocity of the corneal apex, we can use the equation I developed in the last part of the thesis to estimate the intraocular pressure of the patient. And then, by means of the segmentation of the clinical images of Corvis, it is possible to calculate the reduced coefficients related to this patient. So, giving to our new artificial neural network model the Zernike coefficients, the intraocular pressure, and the reduced basis coefficients, the model is able to estimate C10, K1, and K2, with which describe the mechanical response of the cornea, of the corneal tissue. What is also interesting of this process, that the time for estimating the mechanical properties is 48 seconds for all the steps. So I can say that compared to the 48 hours of our simulation, this could be considered real time in clinics. And so to conclude this part, I can say that this methodology is able to estimate the patient-specific mechanical properties of the corneal tissue in vivo and in real time from the result of the non-contact tonometry, which was the main objective of our thesis. But the methodologies I developed for estimating the mechanical properties of the corneal tissue were useful also to study two pathological cases. In particular, the fluid structure interaction simulation of the non-contact tonometer was used to define new indexes to detect the keratoconus pathology, and this fluid structure interaction simulation has been also developed to simulate the implant of a microstent for the management of glaucoma pathology. So I would explain very quickly this part, but regarding the keratoconic pathology, I thought, well, okay, the Corvis give us the information of the deformation of this section, the nasal temporal section of the cornea. And usually, keratoconus is developed in the inferior temporal part of the cornea. So if we study the superior inferior section, maybe we would have more information of this pathology. I mean, we would have a different deformation of this section. And in particular, I propose to study the asymmetry of the deformation of the cornea, because since the pathology arises only in one part of the eye, maybe the deformation would not be symmetric. And so we proposed these indexes, and we simulated keratoconus with an healthy part of the eye, a pathological center with a damaged tissue, and a transition tissue. You can see the mechanical response of the pathological, healthy, and transition tissues here in the plot. Then we tried different models with the different mechanical properties of the pathological area. We defined a template material model, and we recorded the point of highest concavity in terms of spatial position, the position of the highest concavity point for this template material model that was not at the center of the nasal temporal section and not at the center of the superior inferior section, because we had this pathology here. Increasing the material model, that is with a keratoconic tissue stiffer, we found a point of highest concavity more distant from the pathological area center, and vice versa, decreasing the mechanical properties of the pathological area, we found a point of highest concavity closer to the center of the pathological area. So the softer the mechanical properties, the closer the minimum point to the center. This was important because first of all, we are able to study the influence of different parameters, for example, the material, the dimension, the size of the pathology by means of our simulation, but also new asymmetry indexes and section can be studied and proposed to the clinical software in order to detect different pathologies. In this last section, we try to study this pathology, but at the beginning it was necessary to develop a methodology to study this surgery. In this surgery, you can see in the video some 2 stents, micro stents, are implanted in the eye in order to treat the glaucoma pathology. In the glaucoma pathology, the intraocular pressure is too high. For this reason, these stents are used to drain the humor and to lower the intraocular pressure of the patient. In this way, the humor is drained by means of these stents, and the intraocular pressure is lowered. So we developed these pathologies composed of different steps. The implant of the stents inside the eye structure, and the study of the aqueous humor flow after the implant of these stents. And very quickly, I'm going to show you these results. You can see here the implant and the comparison of some CT scans with the stent implanted in the same position. And in this case, you can see the streamlines of the velocity of the aqueous humor flow through the 2 stents, and the fluid pressure, which is decreasing thanks to a gradient of pressure between the outside port of the stents and the inside of the aqueous humor with a very high intraocular pressure. So to conclude, this was only a methodology to simulate the implant of this stent and the simulation of the aqueous humor flow in the stent. And this simulation can be used to and adapted to different situations, different stent, patient-specific cases, and so on. It was only the application of the same methodology I used for the non-contact tonometer more complete to another clinical problem, and we found out that it was very useful for this application. So just to conclude all this presentation, I first presented an FSI model of the non-contact tonometer clinically validated that was useful to propose a methodology to estimate in vivo and in real time the intraocular pressure based on the energetic balance of the anterior corneal surface by means of this numerical simulation. Once we were able to estimate the IOP not influenced by the mechanical properties of the corneal thickness, of the corneal tissue and the corneal thickness, we used this IOP to propose a new methodology to estimate in vivo and in real time the mechanical properties of the corneal tissue, and this was achievable by means of a combination of numerical simulation, artificial neural network, and reduced model. Regarding the application, I quickly presented the definition of new biomarkers for the keratoconus detection using the same simulation, so the simulation of the non-contact tonometer, and another simulation to model the implant of the microstent to the treatment of glaucoma. With this, I would like to conclude saying thank you to my team, from the University of Zaragoza, Professors Jorge Grasa and Begoña Calvo, and from Politecnico di Milano, Professors José Feliz Rodriguez Matas and Giulia Luraghi, and obviously the VPH Institute for awarding me. Thank you again. It's a pleasure for me, and I'm very grateful for this, and all of you for listening to my presentation. I hope you enjoyed it, and if you have any question, please let me know. Thank you.
So you got an ovation. I hope you've heard. Thank you, Elena. So open for questions. Yes.
Hi, Elena. It's very possible that I missed this earlier in your presentation, but near the beginning of the presentation, you described your patient-specific modeling of the cornea, specifically patient-specific geometry, and then later you described your artificial neural network to determine the Holzapfel-Gasser-Ogden material parameters. And you said that with the patient-specific geometry, you were running simulations that were taking upwards of 2 days to run. And that from a clinical standpoint, that's not really viable. But then later in your presentation, you discussed, or you shared that you're able to estimate the material parameters in less than a minute. And obviously that makes more sense clinically. Maybe I missed something, but is there anything that you think that could be improved to be able to run the FE simulations both with the patient-specific material parameters, but also patient-specific geometry, so that it doesn't take 2 days to run, so that you can use it in a clinical setting?
Sorry, I don't know if I understood well your question, but is your question, can we improve the simulation in order to lower the time of the simulation and use it in the clinical setting?
Essentially, yes.
Okay, but I mean, I don't think so, because we have a lot of nonlinearities. And for example, we have the anisotropicity of the tissue, the fluid structure interaction simulation, and this time I think it's necessary for the amount of elements we have and so on. But in reality, once we have our large data set of FSI simulation, we do not need them anymore. Because once we train the artificial neural network, then this is our data set, and then we can stay only with the artificial neural network model and use it in clinics.
Awesome, really cool. Thank you.
Okay.
Okay. More questions? No. Yeah, Elena, I have a couple of questions. The first question is about the assessment of the machine learning, well, of the meta model that you've built with the machine learning. So how do you assess that? Do you assess that so globally according to a specific overall mechanical biomarker?
Sorry, I think I can't hear you anymore.
Yeah, the mic was out of battery, sorry.
Okay, sorry.
Yeah, no, I'm wondering about the validation of, or the verification, better said, of the machine learning algorithm. Are you doing first an independent verification, independent validation? Is that one local according to fields? Are you validating so entire fields of mechanical descriptors? Or are you verifying so a global biomechanical marker?
Okay, what we are doing now is applying this methodology to a large data set of real patients. I mean, we train the artificial neural network with virtual patients. With the mechanical properties and intraocular pressure, we decided and we ran the simulation. Now we have clinical data output of Corvis. So we use this data with the methodology explained to estimate the intraocular pressure, the intraocular pressure and the mechanical properties of the corneal tissue. Then I rerun the same simulation with the same mechanical properties and intraocular pressure and compared the deformation results from the simulation and from the clinical setting. We found out that the results were the same with a deformation error that was not influent in clinics. I mean, the error was less than 5%. So we say, okay, we are validating this methodology in this way.
Okay, but then this is an entire field of displacement or of deformation.
Yeah.
Okay, thank you. And so now I guess that the next step for you is then to be able to see whether with your new mechanical biomarker you can discriminate two populations, right? Control population and next one.
Yes, but before that we need to define the range of mechanical properties, but because as you saw that the range we used for the simulation was very high. I mean, we had very soft corneas and very stiff corneas, and we think that the human cornea is only a little range of these. So first of all, apply to different patients in order to refine the methodology, and then define the biomarkers to discriminate between healthy and pathological patients.
Okay, or maybe you can investigate whether your back calculated corneal stiffness is actually a biomarker that can separate population. Would that be a possibility?
Yes.
Okay. Further question? No? Okay, great. So Elena, thank you very much for your time. And
Thank you
for sharing with us, and then congratulations again.
Thank you very much.
Bye-bye.
It was a pleasure.
Thanks.
Bye-bye.